So we want to visualize high-dimensional data, and our high-level goal here is we want to plot this high-dimensional data as a two-dimensional approximation that results from some linear combination of the attributes of that high-dimensional data. And there's kind of a related goal that we have here, which is we want to make sure that when we look at that two-dimensional plot, it really shows us the variability of the data. If it's not showing us the variability in the data, then we want to be suspicious of drawing any conclusions from that plot. So let's start with a warm-up exercise. So you measure the width, the length, the area, and the perimeter of 100 rectangular backyards, and you generate a table. So here we have a matrix of column width, column length, column area, and column perimeter. So what do you expect the rank of this observed data matrix to be? And if you were to say, well, it's less than 4, what would be the smaller matrices that you could multiply together to recover this data matrix? Now, if you just looked at this, you'd say, well, I know geometry, and I know that the area is just the width times the length, and the perimeter is just twice the width plus twice the length. So rank is 2. I only need the width and the length. But this was a little bit of a trick question, because we need to compute this using linear operations. And we can't compute the area using linear operations since it's the product of the width and the length. While the perimeter is just, we can do that with linear operations because it's just twice the width plus twice the length. Okay, so the real rank is going to be 3. We can drop that perimeter column and then reconstruct it using this transformation matrix. That's this 3 by 4 matrix. So the first row is going to be 1, 0, 0, 2. Second row is 0, 1, 0, 2. And the third row is 0, 0, 1, 0. And so what that's going to do, when we multiply that by our 100 by 3 matrix, is it's going to yield our original 100 by 4 matrix, right? Where the first column will be the width, the second column will be the length, the third column will be the area, and the perimeter will be twice the first column plus twice the second column. So what we want to do is automate this process of being able to capture these redundancies, the fact that perimeter is just a linear combination of the width and the length, and we want to do that automatically. Okay, so this is where singular value decomposition comes into play. So singular value decomposition is a very important concept in linear algebra, and we either assume that you're taking a linear algebra course now or you have taken one in the past. We're not going to explain singular value decomposition in full. So if you've taken 16 series or Math 54, you've seen SVDs covered. So all you're going to need to know for this class is just how to compute it in Python and what it means. So we're just going to look at the output. We're going to kind of basically be presenting things backwards from how you would typically learn about SVD in a linear algebra course. And our goal here is really to give you contextual information for what SVD means in the context of data science, not how SVD works or how to compute SVD. You're just going to use Python to compute it for you and look at the output. So we're not recommending this as your first exposure to singular value decomposition. Okay, so now, when we looked earlier, we saw that we could take our rectangular data and decompose it into 2 matrices. So we had the data without the perimeter, and then we had this transformation matrix that transformed the data from our m by 3 representation without the perimeter and computed the perimeter, so we ended up with our original m by 4 matrix. So there's a couple of things here, right? One, which is kind of cool, is that this is a form of lossless compression. So the total amount of information we need to store is smaller, right? So the original rectangular data set, we stored 100 by 4 values, so 400 values. In our decomposed set of 2 matrices, we have our 100 by 3 matrix, so that's 300 values, and then we have our transformation matrix, which is 3 by 4 or an additional 12. So we only have to store 312 values instead of 400 values. So we've sort of compressed our data a little bit. But this required us to manually look at our data, to know about geometry, and that there was a relationship that would allow us to drop the perimeter and reconstruct it from two of the other columns. So again, we want to automate this process of figuring out what is this decomposition. So singular value decomposition is a technique that will automatically do this transformation for us. We give it a matrix X, and it will return matrix U sigma and matrix V transpose. So let's look at this in Python. So let me get over to the Python notebook, and we'll take a look at this. Okay, so we're going to read in our rectangle data, and we can see we have width, height, area, and perimeter. So we have the 4 columns that we measured, our 4 observations, and we're just looking at the first 5 rows. Now remember, of course, perimeter is just double the width plus double the height. The area is the width times the height, but we know we can't compute that using linear operators. Okay, so we could create a new data frame that just has our width, height, and area and drops the perimeter. Of course, we can recover this by just simply multiplying by our transformation matrix 1002, 0102, and 0010 as each of the rows. And so if we do that multiplication, we get back our perimeter column, right? And so 28, 12, 8, 24, and 34. And if we go back up here, we can see our original matrix was 28, 12, 8, 24, and 34 in our first 5 rows. So we were able to do this lossless compression to go from having 4 columns to having only 3 columns plus our transformation matrix, which allowed us to sort of reconstitute, rehydrate our matrix back into a 4-dimensional matrix. Okay, so now we're going to do this using singular value decomposition. And so given our input matrix X, it's going to return U, sigma, and V transform. And the property is that we can take U, multiply U, sigma, and V transform, and we will get back our original matrix. So we're going to do that. Okay, and so now we've created our matrices. If we multiply them out, we get back our original data. So the 2 key components of this are U sigma and V transform. And so we can think of U sigma as being our data and V transform as being our transformation operation. So let's first look at U sigma. And what we see here is this data. And this kind of looks different from what we had before. We'll come back to that in a moment in our manually derived matrix. Now let's look at V transform. And so, yeah, this also looks very different from our transformation matrix that we had before, which was, again, just 1s, 0s, and 2s. Here we've got negative values, and it's quite different from what we had before. Right now, if we also look at the shape of our matrices, we see that U sigma still has 4 columns. So we didn't reduce it to a 3-dimensional matrix. And our V transform also is 4 by 4. So it's just mapping the 4-dimensional input to 4 dimensions. We wanted it to map 3 dimensions to 4 dimensions. So let's go back and look at this in our slides. Okay, so we can ask the question, what's different about this decomposition from what we did manually? And one thing we observed was that we ended up with our 4 dimensions in U sigma. We did not end up with 3 as we expected. If we look in the upper right, you can see what we ended up when we did this manually. We ended up with a matrix that was 100 by 3, not 100 by 4. Similarly, if we look at our V transform, it's 4 by 4, and we expected it to be 3 by 4. Right? And if we actually look at the total amount of data we're storing, we started with 400 values that we stored. We ended up with a matrix that's 100 by 400, so that's 400, and an additional matrix that's 4 by 4. So we're now actually storing more data than we started with. We started with 400 values we needed to record. We end up with 416 values that we need to record. So there's a number of differences here in this decomposition from the one that we did manually. So if we drill down, we look at it, if we look at the fourth dimension of U sigma, it's all zeros actually, right? And I can go back over here. Right? If we look at U sigma, these last values, right? We have 1.8 E minus 115, minus 15 rather, minus 3.3 E negative 115, again E negative 17, E negative 16, E negative. These are values that are pretty much zero. It's just numerical errors that end up giving us numerical precision errors that end up causing these not to be actually zero. So given that, we don't really need that column. That column's really not adding any value here, right? And so that's one thing that we can see is an issue here is, we have this extra column in U sigma that's not adding anything and is 400 values, rather 100 values that we're storing that we don't need. Okay. The other thing is if we look at the other three dimensions of our data, they're not the width, the length, and the area, right? We've got in the first row, we've got minus 56, 4.1, and negative 0.77, right? And so that's a little off. And then, of course, as we already talked about, the results we get with SVD are 416 values versus 400 values. And if we look at our transformation matrix, it has small values and kind of strange values that are all over the place. So for this data, it's guaranteed that this last column is going to be all of U sigma is all zeros. So we could just throw it away. Now, if we throw that away, what else would we look at throwing away? Like maybe the first row of V transform, or the first column of V transform, or the last row of V transform, or maybe the last column of V transform, so we have matrices that we can multiply out. So think about it. Which of those might we want to get rid of if we're going to drop the last row of U sigma? Well, we can throw away the last row of V transform, right? And so now we have an M by 3 matrix that we're going to multiply by a 3 by 4 matrix, and that will allow us to reconstitute our original M by 4 matrix. And so now the amount of data that we're going to store is 300 values for the M by 3 and 12 values for the V transform. So a total of 312 instead of 400 values in our original data.